and thank you to the organizers for inviting me and organizing such a fantastic event. Are the slides up? There we go. So I'll be introducing Universal Quantum to you and talk a little bit about how we envision to scale up trapped ion quantum computers beyond the NISQ era. Now, it's always great to speak after Quantinuum, who just show how amazing trapped ions are, and I really congratulate them on their amazing results, and we kind of share the passion for the same qubit. I think it really is a fantastic quantum architecture for quantum computing. Now, to start off with, we're a UK-based company. There's around 50 of us, mainly across Europe, south of London and in Germany, north of Germany and Hamburg these days, and we also have a few people in the US. Now, I always like putting this slide up first. It, in a way, is our North Star at Universal Quantum. And here, really, what I want to talk about is when you look at the different applications that I'm sure all of us get very excited about when thinking about quantum computing, when we think about what sort of quantum computer we will eventually one day need to really unlock those applications in a very meaningful way, I think we very quickly find that we have to scale up quantum computers quite dramatically to hundreds of thousands, millions of qubits. And this sort of, it's not a realization, but this knowledge in a way, for us internally at UQ is a major driver to working on ways to scale up a trapped ion platform. Now, just in case this is new to you, the reason we need so many qubits is that all quantum computers have errors. So we need to do something about them. One way is obviously to inherently reduce the quantum gate fidelities, and Quantinuum spoke about that as well. But an additional way of where we really have to go at some point is to do error correction. And error correction algorithms in a simple way are saying, give me lots of qubits, and I'll take care of this problem for you. Very simplified statement there from me. And obviously from a commercial point of view as well, and I take these numbers with a pinch of salt, but really the sort of high-value targets do lie beyond NISQ. As passionate and hopeful that we are, that we can squeeze a lot out of the NISQ era, we do really believe we have to go to the fault-tolerant regime. Now, in order to get there, we strongly believe that we need a modular architecture that really can scale to that sort of level. You've got to have high-quality qubits, and I think that's an important one as well, you have to be able to build it using currently available technology. And I'll show you how we are planning on doing that. Now, in a way, you can summarize our architecture via these three pillars that you can see on the screen here. The first one we've already heard nicely from Quantinuum, how well trapped ions work, how well they are connected. They provide us a fully connected system. We rely on that same chip-based architecture that enables us to do that. Now, here's where it gets a bit different. When we then talk about how to control our quantum entities, our qubits, we're taking an approach whereby we've developed a way to remove many of these laser beams that people often use to implement quantum gate operations and replaced those laser beams, which, if you scale up to the millions qubit level, you really ought to deal with millions of qubits there. We've replaced that with a handful of microwave fields. The key thing here is that no matter how many qubits we will have in our system, the number of radiation fields that we have to send in to control these qubits stays constant. So that's a factor in our architecture that we hope will significantly lessen the burden when scaling up. And number three, really important when people talk to you about a modular architecture, I believe they ought to have a very good approach to connecting individual modules together. That would be a key factor in really being able to scale up, and I'll show you how we're doing that in just a second. Now, these three pillars, they can combine into what we refer to as the Integrated Quantum Processing Unit, or IQPU. And rather than showing you some words, I'll show you a pretty picture of that. What you're looking at here is at the very top, you've got our trapped ion qubits floating above this silicon-based microchip layer, and we like to move these qubits around as well to enable the connectivity between the individual qubits. Now, what we're working on at the moment is to integrate the classical control required to control the qubits on top directly onto the chip. The reason we're doing this today is that we want to get as quickly as possible to a footprint where we have a chip-based module where the things that are required to make this quantum computer work in a way are integrated into that module. So you can think of it like a self-sufficient mini quantum computer. Now, at that point, you now need a way to connect multiple iQPUs together to make a bigger quantum computer. And this is where our technology, which we termed UQ Connect, comes in, which was also recently demonstrated. You can see a picture of that on the left-hand side, right-hand side, there we go, where basically our technology involves engineering the edges of each of these modules in a very special way, such that when we bring these modules close enough together, a special link opens up that allows us to directly move these trapped ion qubits from one module over to the next. No additional engineering involved, no intermediary entity involved to move that information between the two. It's a very clean and comparatively simple method, and we've demonstrated some numbers here. We've got a connection rate of around about 2.5 kilohertz, and crucially, that fidelity, that success rate of making a quantum link between these two modules is near unit fidelity. So it's a very robust, reliable link that we can generate here, and is a key way of how we'd like to scale up beyond individual quantum computing modules. Now, I don't think I need to talk too much about here, but of course, we'd like to also at some point distribute our quantum resource via the cloud. We're deeply integrating at the moment with classical HPC computing to provide a seamless experience for the end user, like many other hardware companies are doing as well. Now, I talked about the manufacturability of our solution. This is key for us. We've worked very hard to make sure that everything that's required to fabricate the iQPU is based on standard fabrication technologies that we can access today. In a nutshell, the fabs that we work with don't really need to know about us, which is actually, in my mind, a very good thing. And just in case you don't know the advantage of trapped ion systems in general, we do not need to cool down to millikelvin temperatures. It's one of the reasons why we can even think about doing that integration of classical control into the chip layer. So we're operating roughly at 70 Kelvin. Now, just a quick nod to the UK government. On the commercial side, they've been very supportive of us, in particular the project there on the left-hand side, which we're leading, where we're building the UK, an error-corrected, scalable error-corrected quantum computer company, and also not to Riverlane, who I'm sure are here, who are a close collaborator, and I think may even speak straight after me. Together we're really developing this technology for the UK. And very recently, the German government has purchased 2 of our quantum computers and a major supporter of our technology. We've won a contract just under 70 million euros to, one, deliver a quantum computer based on this iQPU single module technology. And then they also got very interested in how we're connecting these modules together and have purchased our first multi-module quantum computer. Now, we're not just, in a way, passing a quantum computer over to Germany. We're really also developing an ecosystem around those machines locally. So these machines will be built at the facility of our customer, and we're really building that ecosystem around, which we think is really, really important if you do deliver quantum computers. So with that, I finish, and I think I have 1 minute left for any questions, if there are any. Oh, there, very quickly there.
Many thanks, Sebastian. Can I ask two quick questions? So one, do you think it's important that quantum computer suppliers supply an open package that can be accessed, not a black box, not a closed back box to overseas governments such as Japan? And secondly, what sort of companies would you like to talk to while you're here in Japan?
Yes, I think we try to be as open as possible. I think for hardware players, it's not always as easy as for software players. But I think especially on the software, in terms of how these machines get controlled, we do like that collaboration a lot. And on the hardware side, we do collaborate with a lot of suppliers, and naturally are quite open there anyway to make sure that we leverage the expertise that many companies already have around the world. So we do open up there as much as possible, but there's also very key IP that we obviously have to retain, and an entity like Germany just has to accept in a way that particular small black box. But we are as open as we can, and we do like to collaborate as much as possible. I think someone mentioned that before, that to build a scalable, large-scale quantum computer, it's not just done by one company. It needs to be an ecosystem that really drives that forward. And the second question?
And what sort of Japanese organizations would you like to speak to here?
Yeah, so we already collaborate with some fantastic suppliers. That's already a big part for us, but we'd also like to talk to potential end users and potential collaborators who share our vision in terms of where we need to go to eventually, and in a way grow with us as we